Alright, so, do you guys, just to get started, did you guys decide upon one method of doing it or multiple ways to do it?
We talked about at least like a solid two, I would say.
Yeah.
Yeah.
Two, we kind of hashed out the steps on. One, we really dove into the problems that it might have, and we came up with solutions that would fix. We have some problems with our second method that we could talk to you about. We thought you might have some answers for us, but most of these slides relate to just the first method that we're probably going to roll with because we have an idea of how to implement it already. So this was the example we were mostly looking at for our first method. As you can see, it mostly has a slant and then it kind of evens out and it becomes more linear as you go down the page. First things first, a problem that is existing in both of our algorithms are these vertical lines and also horizontal and lines that appear on the bottoms and borders of a page. So we were thinking about, that's the first step, is culling those out with a recursive algorithm that just looks at the neighbors, and if I can find a vertical or horizontal line that spans more than 25%, 50% of the page height and width, respectively, cull it out. Because there shouldn't typically be lines of text that span more than 50% that are continuous. So, under our algorithm, after we have that, we want to find the first box. So we're assuming that we got this line. We're skipping to the first one. Our box, we first start with the starting point. We're reading top down, left to right. So we get the highest point, and then we have a method to calculate the height and width of that box around the first character, the first continuous character. And then from there, that'll be our buffer size, and we're going to either move our buffer size right and up a little bit, or right and down a little bit. And then we're going to pick what box we select out of those three options by density. So since the density is, oops, I'm losing my mouse a little bit here. Since the density is like mostly allocated in the first box here, it should select that one. And then we would move the buffer along until the buffer is completely empty, which would occur over here, or until the buffer is completely empty. I think that is our only stop condition right now. And then, so we would draw a complex polygon around these buffers using the points from these boxes that we draw around. But we would just end up taking the box that we would submit to the website, would be the top, bottom, left, and right most points of that complex polygon. But the reason we want a complex polygon is to zero out all the text that appears in here in the Canny image. So I kind of skipped over this in the beginning. We're essentially reading the Canny image into a binary array, so we can zero out pixels as we go along, because we can't really zero them out in the actual image itself. So we read this whole thing into a binary array, and after we draw a complex polygon around the text, zero out those pixels. So now when we continue to read on, we'll continue from this point, but it won't hit any of these pixels until it hits the eye here. So it'll draw a box around this eye, and that'll be the new buffer size, and we'll walk it across along, and it might stop here, but so we have to do some tweaking with the buffer size. If it is too small or too thin, we might take the first two characters of white text, and that'll be our buffer size, and slide it along. But then we came across the issue that, well, we have all this text. The eye is the next highest point, yes, but there's text for the rest of Resurrection that appears on the left. So we'd also have to scan to the left to detect any text that appears to the left of the highest pixel in the next line. So essentially, if there is any text to the left of this, you have to jump back and scan to the left as well, and increment that to the complex polygon. Does that make sense so far?
Yeah.
Yeah? Okay. So that's basically the gist of the entire algorithm. The stop condition is, for the row scanning, is when you hit the bottom, you go to the next row and you're scanning left to right, and you hit the bottom of the image. And that is essentially the stop condition for that. And that's the gist of the algorithm.
So why'd you guys go, why'd you go for the method of selecting, so to get started, you're choosing a rectangle, square that supposedly contains a character or some
Yeah.
feature?
Yeah, a character, or if it's like a word that is continuous, like there's white pixels that span the entire word.
What is not a word?
Uh,
It's not a character.
If it's like a hieroglyph, then it will take this. It will take the size of that hieroglyph then, because the method that we're going to write is like it just calculates the space of this character that it takes up essentially in the image. So it's going to grab the topmost point and the bottommost point of the T and the left and rightmost point of the T, and that'll be the buffer that we're moving. If it is a hieroglyph, it'll do the same thing for the hieroglyph, assuming the hieroglyph is continuous.
Well, you can't assume that. You can't assume that. I mean, so we've been working with text. That it's very naive to believe every language, every language process is going to be as consistent as the English language and the character set that we work with.
Mm-hmm.
Hieroglyphs are different sizes, different widths, vastly different than what we're working with here. So that algorithm would immediately fail. I can see where a small hieroglyph is next to a really big one. If you're choosing it based on the first one you run into, it's gonna be a non-working algorithm. So can't make an assumption about what it is we're detecting. Did you guys come up with any other ideas for how to approach this problem?
We came up with a waterfall algorithm, which is kind of like what you talked about before, where you still read top down. You still read top down and you catch the topmost pixel and you sprout essentially an umbrella over the top of it, and you keep drawing. Oh geez, this mouse is being weird. So if you can imagine an umbrella over the Y here, because it'll be the topmost pixel, we sprout the wings of the umbrella and we drop rain from the edges of the umbrella, and if it hits a white pixel, sprout a new umbrella and continue until you hit either the width of the page or the rainfall drops a certain amount, in which case you've probably hit either a column or the end of some text at least, or you've dropped down to the next line, which we thought about. And so even if I drop this far, if I drop more than the average width or the average rainfall distance, move the buffer or move the edge of the umbrella over some arbitrary distance. We thought 3 pixels might do it, and then drop rain again. And if I continue to fall, then I know I'm probably in a space. And then that gives you the.
Put some code for this, or is this just a
For this thing,
image?
this was just kind of to visualize it. I wrote a quick thing that drew lines every few pixels.
Yeah, this is arbitrary. It's not really going. It's not picking the left pixel here or anything. It's just every 16 lines or something. Every 16 pixels, I think it is, or 32. But yeah, we haven't put anything down in code yet.
Right. So explain this a little bit more. You're gonna let's see how would your algorithm work over here?
Well,
Rainfall.
yeah. So we would still do our vertical and horizontal line culling thing over here, because in Canny these page borders still show up. So this ideally, assuming that the top of the A is above the 6, I don't think it is, but assuming it is, it still grabs the top pixel of there. So it would make a umbrella of this width to these 2 blue lines around the A, and it would drop rain from them. And assuming that I hit a pixel, or if I hit a pixel, then I sprout a new umbrella, and I continue the cycle until I hit an umbrella that is either holding no text, or I drop too far. The rainfall drops too far. And then that grabs the top line, and the bottom line is kind of what we're struggling with. That's kind of why we went with the first algorithm, because yes, it's all fine and good when you're getting the top line, but when you come back and you have to get the bottom of a line, how tall do you draw the umbrella so that it only catches the row that you're on and not the row below? Because we don't know the row heights beforehand. And we can't go by character height because it fails for the same reason our first example fails. Did I miss anything, guys? No.
So did you guys draw these circles or just go over your previous algorithm?
This is from Paint. Yeah. Columns, because of all those vertical columns, ours bus, I think theirs bus sort of, they catch the bottom left corner of the Bible and draw a box around the entire text. So I think, yeah, this is where theirs is actually roughly.
Yeah, that's what ours roughly looks like with the yellow.
Yeah. It catches this big box.
So that's what we want to basically basically add to the, each of the algorithms, like whatever, the counter's a big space like this, so you chop it up into rows, because right now, that's the challenge. Because your algorithm should already take care of the page border crap at the edge, you know? And I throw those out already. So you should already be doing that. I don't know, let's go back to the first method, talk about that again. What image did you actually use in this one? I'll let you.
Okay.
use the mouse.
Oops. It was the top one. There it is. So yeah, that is a big assumption. I guess we just kind of thought that usually the first character won't be that vastly smaller than the next character. That was our big assumption. Because I mean, even if the rest of the letters in this were capitalized, and this first letter was like a lowercase o or something, it's still, the buffer is going to be set to that size, and it's going to pick the density of whatever highest is from those boxes is.
Yeah. So, what's what are the monks?
Yeah, we thought about this too. Like if the first character is like like a fairy tale letter, like it is in a lot of old fairy tales where the T is giant and the or something like that, then it definitely breaks, and we'd have to cut columns on that big block of text.
Okay, so you can't assume the size is gonna be the same, it's just a bad assumption. So you could probably still make it work. You can't think about the size of the character. There are no characters, there's just shit on the screen. Let's call it a feature. We don't
Okay.
know what it is. Could be like a mark from Bloodstain, could be a character, could be hieroglyph, there's just some shit on the paper, we have to figure out what it is.
Yep.
Close it down. So you don't know the width. You can probably kind of determine the height, but again, the height, the first couple pixels of a row can be extremely different than the following. So if you determine the initial height, you could start proceeding horizontally, but you might have to adjust the height upwards.
When you say that, do you mean adjusting the height of the buffer that we're sliding across dynamically as we scan the row? Or are you saying,
Just create this. So I'm gonna do super awesome job. Over here's the first width you detect.
no, it'll be,
And across the row could get bigger, the text could get bigger, this could be dot, 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 and the key length forever. You gotta run into the dots first, which are really small. So if you're scanning, you would use this initial height that you find as the rule to use moving as you move horizontally. It's a false assumption. So what you need to do is as you move continuously, determine the height basically of the non-white space, the non-background color, and adjust that. Keep that going. There could be, there's gonna be white space in between it, but basically, you've got to scan up and down and increase that. Increase the width a little.
Yeah, we
height
could
a
adjust the
little bit.
buffer height based on the same idea with the first one, just do it every single iteration.
example right here.
So
You
it,
start hitting the periods down there, you have to be able to increase.
because we do top down though, it'll grab the L because it's the leftmost pixel, and that'll be the size of our buffer, and then we'll slide that along. And if the buffer is too small, then we extend it to the next character as well. So it'll grab that and the T. So it won't ever start at the leftmost character unless the leftmost character is also the highest character. Does that make sense? So like, if this, we could just throw a pixel buffer on here on the L, say it's got to be such a box has to be such a width of the image that, like if this is less than, I don't know, a billionth of the image width, then connect it to the next consecutive character. So it'll span the T, and then it'll slide this box along. But it'll never catch these periods because they're not the next highest thing. And we'll just scan the buffer across this way, and then when we get the consecutive white space over here, then we'll return to our start position and scan the other way. And that's how we determine the complex polygon. So if this small was curving downwards, the buffer would also move downwards because the density would be higher in the lower box of the three options.
So if you've got two columns of text, your algorithm would hit here first because it's the topmost.
Yep. And the buffer size would be the width of the B and the height of the B. And that would be the buffer size, and we'd slide it across until we hit an arbitrary number of empty buffers, and then we'd restart and scan left.
So how do you plan how it reset to keep going down consecutive rows of the text then?
So that's where the binary array comes in, because our complex polygon will catch all of this text, because those will be the corners of our buffer. It'll all get zeroed out in the binary array. We'll start back at this point. All this stuff will be 0. It will continue to read until it hits the I. The I is too thin, so it attaches the O with it. That's our new buffer size. The buffer continues to move. The density starts to get to the lower box. It shifts to the lower box, and we're adjusting those points in our complex polygon as we go. We slide down. We hit over here. We have an arbitrary number of empty buffers. We restart at the I, and we start scanning leftwards. And then when we're done with that, of our complex polygon, we take the top, bottom, left, and rightmost points, and those are our box, which is kind of what you're seeing here, this yellow box. And yes, it catches a bunch of this stuff, but that's because we are choosing a box and not a complex polygon. But so then our next box would look something like the top of the I, because it's the next highest most pixel, to the bottom of the whatever's lower, the bottom of this Y, it looks like, over to the O here. So this box, from going corner to corner.
Are you guys on board with that method?
It's the best one we have so far, I think.
This is the method we spent the most time with, and all the other methods we're doing more pixel by pixel comparisons rather than a density check. So this is like checking the density of each of these boxes rather than pixel by pixel comparison. Because eventually we went back to the idea of that staircase that you first introduced for the complex polygon idea. But the thing is, sometimes, say I hit this O and the understanding is too far away, I'm going to staircase down until I hit the next line if the next line reaches up high enough, which is an actual example in like, it actually happens in this example, where it's so tight together, the hanging M, whatever this letter is, kind of reaches down into this area as well. So it's too low.
So I'd say go ahead and start working on that. I would instead I would just return your complex polygon. Let's actually see what it looks like on the website. And since we're trying before we convert it to a regular simpler rectangle. So you guys need a plan so that one of you isn't the coder and a bunch of people are just sitting around looking at code on the screen somebody else is typing.
Yeah, I think we're.
That's the way to this through the other week, include multiple files, you should be able to work on a portion of it. Cool. So when do you guys think you can have a working mock-up?
You gave us till next Friday?
That's like, it works for everything. Next one, I'm just kidding.
You could do next Friday, probably.
Okay.
We have a bunch of recursive functions in here, or not a bunch, 3, I think. We wrote our helper functions down. It's in here too.
It should be on the picture of the whiteboard.
Yeah. Let me open that back up.
Somewhere else.
No, it's the old one.
There you go. Helper functions right up there, if you can even read it.
So yeah, find neighbors is the method that we're going to call a couple of times. It just looks at the neighbors around a black pixel and tries to find a path that it can follow, and if it can follow that for more than 25% of the image width or something, it'll throw out, because it'll be a vertical column or a horizontal thing, roughly. And then is in poly is what we're going to use to, so if there is a letter that hangs outside the polygon, like this P here, oh no, that's not a good example.
But are you talking about inside your complex polygon?
Yeah, inside our complex polygon,
Then there shouldn't be anything hanging out, right? Because you're tracing everything. You only have
What was
issues
it?
with things hanging outside when you convert to a rectangle and something. Correct.
what was that? I thought we had an issue.
Well, yeah, it depends on what, when we pick the box with the density that we want to go with, then it depends, like, weren't we just originally going to like draw or take the points like at the bottom of the box and put that in the polygon? And then that was why stuff by taking it out the bottom of.
Oh yeah, so yeah, so if it picks this box and there is text down here, like if the G, most of the G is in this box and then the tail's hanging down here, it will pick the middle box. So that's why we have to do call perimeter, because if there's so much a percentage of the character that is inside the box, go back and adjust the complex polygon.
Well, was that how it, because the way that I remember us talking about it was like, once you decide, you pick whichever box has the highest density, and then you move, like that becomes like your new current box, and you look in front of that. That box, just because it had the highest density, doesn't mean it encompassed everything that was in that line, and you might have like letters that had lines sticking out below it.
Exactly.
So that was what we were gonna use, like the check perimeter and then like follow neighbor pixels for, so that if we
Yeah.
had something that crossed the line of that box and more, and we could tell that it continued to something inside the box and more of that continuously found line was inside the box than outside, we would zero it out with the rest of the things inside the complex polygon.
Yeah, if most of the G is within the box, then we'll zero out the tail. Else, that's its own line. We continue to read from there on the next one, because it'll be the next highest point, probably.
So how would your algorithm deal with?
That one with the string hanging down? Yeah, it breaks here. We'll have to do additional row cutting here. But
Yeah, so right here, what would you do with this image?
so ideally these will be called, so we'll just be looking at the text.
How are you gonna call
Right.
them again?
The find neighbor thing, if it's greater than, yeah, neighbor and continuous lines. So then it'll come here, depending on how we write the, choosing the first buffer size. It'll either grab this line or these two, and then it'll slide the buffer along. And since we didn't hit consecutive buffers of emptiness, we know we're not at the end of the page, so it'll continue to do this. You're talking about stuff like this, though, right? The hanging down stuff?
Just in general, I guess.
Yeah, so this buffer will continue to write, and because most of the density will be in the center box, not the bottom or the top box, it's just going to continue to slide along until we hit the edge of the page, and then it will reset and go to the next highest pixel. And we also have a check, something I didn't talk about before. We have a check, so we have to have at least so many buffers filled with stuff of so much density for it to be considered a box or a complex poly. We have to have so many buffers in a row. So like this stuff over here, this will be set to a box originally. It'll look to the left and the right. Because the density is too low, then we don't draw the next buffer or whatever. So it'll look to the next one and so on.
So like, after you process the first line of this, and you drop down, you say find the next highest pixel. Where in this image is the next highest pixel?
Assuming we called the left stuff, and if we've called this stuff, it'll probably be this guy. Assuming this is higher than this. If this is higher, then it'll grab whatever continuous chunk this is.
So you're just having like, as you put your first line of text or whatever into a complex polygon, and keep track of those lower coordinates of that polygon, and you're from there, top down scanning to find your next.
Not from the lowest, we're going back to the highest because everything in this box should have been zeroed out. Everything in our complex polygon should be zeroed out.
Oh, so you're actually changing the bitmap.
Bitmap, yeah, that's what. Essentially, yeah, the binary array of the candy image, essentially a bitmap. This is all getting zeroed out on the second pass. Everything that is in the complex polygon. So then we'll continue to read down, and it'll catch this, and it'll do our buffer algorithm on it. It'll die because it's not dense enough, and then it'll go to the next thing. This will be zeroed out in the binary array as well. So ideally, when we hit the bottom, everything will be zeroed out. And we'll just have our boxes and complex, we'll just have our boxes left, or our complex polygons if that's what you want us to return.
Sounds like a plan to me.
We can ask?
So what I'd probably do for this, so what's the plan? Are you guys both the Bronco and Charlie teams? Are you going to take this code and put it into each of your current algorithms?
I tried to do well, I don't think this is going to be easily incorporated into our stuff. Just because of the way we're doing stuff with density, we're checking density lines linearly. So
It's a brand new one for you guys.
ground up, pretty much.
There's tools that we've created for our previous one that I think will be very useful here that we've already created, but the primary function that does everything that one will need to be written from scratch.
Okay, so just call a different, the different area function. So area function equals whatever, like columns, call curve, break
Yep.
up the code for this into a separate file, separate functions. Don't mess with the original stuff.
Right on.
Cool. All right. Good luck, guys.
Thanks.